moderator. What is moderator? मॉडरेटर होता है और एक क्या होता है, कूलेंट होता है. तो कुछ केसेस में कूलेंट भी होता है, मॉडरेटर दोनों सेम होता है. कुछ केस में कूलेंट अलग होता है, मॉडरेटर अलग होता है. तो व्हाट इज कूलेंट, व्हाट इज मॉडरेटर?
कूलेंट तो
कूल कर रहा है
उसको,
हाँ
ठंडा रख रहा है वेसल को,
हाँ
उसका टेम्परेचर एक्सेस होने से.
हाँ. मॉडरेटर जो है वो जो न्यूट्रॉन आ रहा है बाहर, उसका वेलोसिटी ज़्यादा है. ठीक है, तो जब वेलोसिटी ज़्यादा है तो उसका क्रॉस सेक्शन कम होगा, तो इट विल नॉट बी रिएक्टिव. So you want to decrease the velocity of the neutron. In decreasing the velocity of neutron, in some cases like in fusion reactor, you also absorb heat. Energy absorb करके heat में change करता है. तो fission reaction में if it is thermal neutron जिसको बोलते हैं, जिसका एनर्जी कम होता है, वहाँ पर लाने के लिए there are moderators जो उसका एनर्जी कम करता है न्यूट्रॉन का. So some chemical reaction goes on which I am not so sure. Neutrino आता है, बाहर नहीं आता है, but that is the job of moderator. So graphite is a moderator. Used to be, so Chernobyl में graphite था, और PHWR में heavy water है. So ये जो न्यूक्लियर रिएक्टर इंडिया में बना है वो इनिशियली कनाडा के हेल्प से बना था, and then India started developing its own PHWR. अभी इतनी कैपेसिटी है कि वो आसपास की कंट्रीज को PHWR सप्लाई कर सकता है. And now they are moving towards some other technology. Yeah. So heavy water कहाँ से आता है? कहाँ से आता है? पहले तो heavy water भी कनाडा से आता था, पर heavy water तो sea में होता है, sea water में heavy water होता है. Okay. So in this PHWR you have these tubes. Also in the Chernobyl reactor there were tubes. So tube के अंदर you have another fuel tube. Fuel tube is of zirconium 4, zircaloy 4. उसका बना होता है, उसका स्ट्रेंथ ज़्यादा नहीं होता है, बट उसका न्यूक्लियर प्रॉपर्टी है ऑप्टिमाइज्ड. So fuel bundle is inside, uranium and all those things are inside. Reaction takes place and then you have pressurized heavy water. So उसका boiling नहीं हो. If you don't have pressurized heavy water, then you will have boiling water reactor, PWR. Okay. So we were discussing yesterday this equation. So instead of writing K1C, I have written KJC. Okay, KJC means that you are getting K from J. Okay, so root over J square each time. This is what KJC will be. So you are actually not calculating K, you are calculating J. And then you obtain K, so that becomes KJC in literature. And some of the researchers have problem with this, so they don't really want to call it K because they don't believe that it is K, because it is not coming from the theory of K. So this equation is applied in the range of ductile to brittle transition, and if you plot, let us say, Charpy energy for BCC materials and for FCC materials and for HCP materials, then you get something like this. So this is for FCC, this is for HCP, and this is for BCC. Okay. So with increase in temperature, the energy absorbed for fracture will increase because material will become ductile. And that can happen because of different reasons. In FCC, for example, you have 12 slip systems. Okay, so in FCC, the slip plane is 111 and slip direction is 110, the family of this. And a combination in one unit cell gives you 12 such combinations, and therefore you have 12 slip systems in FCC. In BCC, you have 48 slip systems. Okay, and there the slip plane changes, slip direction is 111. And in HCP, you have 3 or less than 3, sometimes 2, sometimes 1 slip system. So this is why HCP will not give you that much toughness. So magnesium will not give you that much toughness. Zirconium will not give you that much toughness. And all FCC, aluminum, what other?
Magnesium.
Magnesium is FCC.
Nickel.
FCP. It is FCC. Nickel is FCC. So these materials will give you very high ductility. And BCC shows a change in energy absorbed from lower temperature to upper temperature. So with temperature, it is not constant, it increases, because it is not just about slip system. Even if you have slip systems, this location, they move when they get blocked. So if you have cross slip happening, if you have a possibility of climb, and these things will increase with increase in temperature, vacancy, equilibrium number of vacancy will increase. So climb will be possible, and therefore block dislocation can move. Okay, so with increase in temperature, you will have enhancement in the toughness of the material, because material will be able to take more deformation. So that you can see in FCC and HCP both. Okay, but in BCC, apart from this, you have a change in slip system with temperatures. So these 48 slip systems in BCC are not at once active. They get activated at different temperatures. So different slip planes, they become active. What does that mean? So you have different planes with different atomic packing fractions. So different number of atoms are sitting adjacent to each other. So the one which has the atoms which are closest, on that plane movement of dislocation is easiest. Okay, that's why on 111 plane, which is the closest plane in FCC, you have, that is the slipping plane. Okay, and you have enough of those planes. In BCC, none of the planes, if you can calculate the atomic packing fraction, which you should have calculated before, if you do that for BCC, then you will see that none of the planes can match the atomic packing fraction of 111 in FCC. Okay, so that plane which has closest value of packing in BCC will be active at the lowest temperature. And as you increase the temperature, the tendency, so the movement of atoms becomes easier for larger distances. So even those planes where atoms are little far away, there also dislocation movement becomes possible. So that's why with increase in temperature, you can have increment in slip system in BCC. So all together they are 48, but not at once. Not all of them are active at once. So as you go down in temperature, less number of slip systems will be active, and vice versa. In HCP, you have basal planes. So 112 bar 0 or 1000. These planes will be the slip planes. Sometimes you have pyramidal planes where slip can happen, but that happens with change in temperature. Also, HCP shows different slip systems with change in temperature, but even then it cannot match BCC or FCC. So the overall toughness is smaller in comparison to these. So problem is not with FCC or HCP. Problem is with BCC, and then the most applicable material is steel. So ferritic steels, they undergo this problem, and the ships and all those things whatever component you make from ferritic steels, if the operational temperatures are in the range of this temperature, so if your operational temperature is below this or in the upper shelf, then you don't have any problem, then you are okay. But if your operational temperature, if your pressure vessel or ship is going to be in marine where the temperature is negative, and then obviously it is going to move, so then you will changing the temperature, so the toughness will be changing, and then you have a problem. So you need to take care of the structural integrity of the component. You need to ensure that it will not fail. Okay. So this is a fitting line. They really don't look like this. I told you in the previous class that if you take data, you will have a huge scatter, and I also told you the region of scatter. So this sigmoidal curve is found by fitting the overall data, but the real behavior can be very different from this. So you are really not sure. So what you do with this statistical problem is that you take a 95% tolerance bound and 5% tolerance bound, and then you ensure that you have 95% probability of failure or 5% probability of failure. So if you are going to be very conservative, you will keep your design criteria less than 5% probability, and then you will be kind of sure that nothing wrong will happen. So with this, when you plot, instead of Charpy energy, if you plot K, then also you will see this kind of scatter that we discussed, and then following Weibel's distribution, 3-parameter distribution. What are 3 parameters here? One parameter is K naught, another parameter is K min, and third parameter is this N, which Weibel decided N. That value we found that to be 2 because it scales with the active plastic volume, which scales with B into K to the power 4. Okay, so N is 4, that is solved. Now we have 2 parameters to solve. So, and then there is no temperature here still. Okay, still there is no temperature. So K minimum is the value of the stress intensity factor below which brittle fracture cannot happen. So obviously it cannot happen below 0 or at 0 also. Okay, so at 5 megapascal also probably it cannot happen. So people found that while doing the testing, they do fatigue pre-cracking, and in that fatigue pre-cracking, the K max goes to 20 MPa root meter. Okay, and while fatigue pre-cracking, although that is happening at room temperature, not at lower temperature, so the fatigue pre-cracking can go higher than 20 MPa root meter. Okay, so after a lot of analysis, people arrived at this value that if K1C or KJC is lower than 20, then we don't expect the material to fail. Okay, so that is hitting lower shelf. In lower shelf, you don't have much scatter here. Okay, and also in upper shelf you don't have much scatter. The scatter is mostly in the ductile to brittle transition. So then K minimum becomes 20 MPa root meter, and now the problem is, what is K naught? So K naught is a reference parameter that you can find out what K naught will be. So then you have to put KJC is equal to K naught. Okay, so then ln of 1 by 1 minus PL to the power 1 by 4 will become how much? So if you put this is equal to K naught, so then this becomes 1, right? So exponential minus 1, then 1 minus PF, ln of that is equal to minus 1. Then you take this, okay? Then that becomes 1. Right? Whatever is the value, 1 by 4 or not. So because there was 4 here, so instead of putting it 1 before, you do this operation. So then you have exponential negative of whatever function to the power. 4 exponential will go away. So then you take 1 by 4 here, and then you take negative out by reversing the function. So then becomes this equals to 1. So what will be the probability then? What will be the value of PF? So 1 by 1 minus PF will be equal to how much?
0. Wait, sorry.
ln1.
LN1.
ln1 is?
0.
ln1 is 0?
Yes.
Really?
Yes. LN1 is 0. But this is 1. So
E to the power 1.
E to the
So e to the power 1 is how much?
2.732.
2.732. 2.732. So then PF becomes 1 minus 1 divided by 2.732. How much is that?
1.732 divided by 2.732.
Let's check.
Yes, sir. 1 by 4 power
1 by 4 पावर तुम कितना भी डाल लो 1 पे.
सर 1 by 1 minus PF तो आएगी.
हाँ उधर तो 1 है ना, इसको उधर डाला तो 1 ही हो गया ना.
नहीं आगे आ जाएगा ना.
पावर आ जाएगी सर, e की पावर पे जाएगा.
e raised to power 4 हो जाएगा इधर.
क्यों?
सर ln
के
अंदर.
हाँ correct. So then it will become 4. Correct. Then it will become 4. But do I need to do that?
e raised to power 4 होगा सर.
Yeah. But do I need to do that? Just so if I put this is equal to k naught,
ये से तो पावर तो यही होंगे.
पावर तो यहीं खत्म हो गया. ठीक है. So
यहाँ बचे नहीं.
then how much do I have? ln of 1 minus pf will be equal to minus 1. So ln of, so this I don't need them. So 1 by 1 minus pf becomes 1.
तो 1 हो गया.
Then this becomes e. How much is 1 by 2.732?
0.366.
0.36. So 1 minus 0.36 is
0.633.
0.63 something. So k naught is the value of k when you are hitting the probability of 63.2%. Right? How do I get PF is equal to 63.2%? By putting KJC is equal to k naught. So when k becomes equal to the reference value, then you will, whatever probability you get, that will be 63.2% probability, right? So KJC at 63.2% probability is equal to k naught, right? Isn't it?
सर ये एक्सप्रेशन कैसे आया सर? ln 1 minus PF is equal to minus 1.
What?
ये first
From
वाला
this,
-1 कैसे है?
in this equation, you put KJC is equal to k naught.
yes sir.
Then what happens to this part?
0.
0 कैसे?
होगा ना?
K naught minus k min
One.
by k naught minus
One.
k min is 0. 1.
1.
So 1 to the power 4 is
1.
So now you have 1 minus exponential of minus 1, okay, is equal to, so PF is equal to this. So take it that side. So 1 minus PF is equal to, so
Okay sir.
this, okay. And then we need to introduce in KJC, we need to introduce temperature dependence. So this KJC value is temperature dependent, and the physics tells that there are some, so the phenomena of brittle fracture has certain components which are not dependent on temperature and certain components which are dependent on temperature, okay. So for example, the distribution of carbides or secondary phase is not dependent on temperature, right? but the number of carbides of secondary phase which can become cleavage trigger or brittle fracture trigger points, that is a function of temperature. So if you have, let us say, in the active plastic zone, so here in this volume you have n number of carbides. Okay, so if you are at lower self, all of them probably has the tendency to turn into micro cracks, because matrix is going to deform in the brittle fashion. As you increase the temperature, matrix gains some ductility with temperature. Okay, so then those carbides which are really at the crack front, so let us say that this is the crack front and you have 4 carbides here, and other carbides are lying away at certain angle and also on the theta is equal to 0 plane. So those which are exactly at the crack tip, they might have highest probability of turning into micro cracks. Also constraint will play a role. So if you have higher constraint at the center, there the material will have a tendency to fracture in brittle fashion more in comparison to those which is at the surface. Okay, so carbides which are there at the center will have a tendency to turn into micro cracks. The maximum principal stress, if you plot, that has a behavior like this. It is not like this. So the maximum principal stress in plane strain condition attains a maximum value a little away from the crack tip. Okay, it doesn't matter where it attains maximum, wherever the maximum is, there you will have maximum probability of these carbides to turn into microcracks. So not all N are going to help in brittle fracture. If 4 of them or 5 of them, they create microcracks, and those microcracks locally increase the stress even further because those are microcracks. So then those microcracks will just open up and join each other, and they will become a big crack and it will open up, and you will have a brittle fracture. If the matrix can have some ductility, then what will happen? These microcracks the matrix will deform surrounding to these microcracks and they will become void. Okay, so their ductile damage will happen. So this is a function of temperature. This changes as you go higher in temperature. More number of carbides will have a tendency to turn into voids rather than turning into microcracks. Okay. So fracture toughness will have some part which is not a function of temperature, and certain part which will be a function of temperature. And then you can write a function which can define KJC like this. So if the total is A naught, then A naught minus A part is contributing to thermally activated phenomena, and certain part is contributing to athermal contribution. Okay, and C is a constant. A naught is, you have to keep some value of A naught. That's the reference value of fracture toughness. And T is the temperature, and T naught is the temperature where this value will be attained. Okay, so when again with a lot of experimental work and discussion, the KJC value, so A value or E naught value comes out to be 100 ampere root meter. So we want to know what happens, or we are interested in a temperature where KJC attains 100 ampere root meter. Okay, so in that case some value of A must come, and 100 minus A will be here, and then you will have some value of C, and all these things you have to find out. Okay. And how do we find those? In order to find that, we use maximum likelihood analysis. And maximum likelihood analysis takes the probability distribution function, which is the derivative of the probability with respect to the variable. And then you take survival function, which is simply the exponential part of the probability distribution function. So exponential of minus kjc minus 20 by k naught minus 20 to the power 4.
Sir, in that equation,
So if
sir,
yeah,
sir, in that equation, the unit of C is in the form of temperature, degree Celsius or Kelvin. To balance the units.
balance the
C.
unit. Okay, let us balance the unit. So C will be a fraction, and that will be delta t. Exponential of delta t will have what unit? So that becomes, yeah, C is a constant. This will have a value of degree Celsius, Kelvin, whatever. Exponential of that becomes irrelevant. So then you have the unit of ampere root meter
Yes, sir.
plus ampere root
Ampere
meter
root meter.
is equal to ampere root meter.
So whole term must be unitless.
Yes. Because you are taking exponential, so that this is going out. Okay. So probability is something. So this is the probability of failure. So 1 minus this will be probability of survival. So that is your survival function. Okay. And then the maximum likelihood parameter L is calculated as oh sorry 1 minus L. And delta, I'll tell you what delta is. So how do you do it? You do the fracture toughness testing at different temperatures and you generate a lot of data. Okay? Because for statistics you need data. What you could do is that you can take such data and you can do machine learning these days. So you don't have to go there. Okay? So one of you might try doing machine learning on this, if you know what machine learning is, or if you can take this data and then, so I can supply you the data. A lot of data is there in open literature. So what happens is, like, suppose I have tested at different temperatures. So I have kjc value, a lot of values. So at one temperature also I do more than one number of tests. Okay. So let us say at T1 I do 2 tests, T2 I do another test, and so on. Okay. So then I have I is equal to 1, 2, 3, 4, 5. Those are i's. Okay. So then I take the expression LPF by, so dPF by dkjc. There you don't need to put the values. You can just find out from the expression, that expression, what will be the derivative. Okay. And in that derivative value, you keep that derivative value. So you keep this and then you have this. You multiply these two. Okay. And you put the values, each value there every time, and you sum them up from I is equal to 1 to n, whatever is the value of n. You sum them up and then you put that equals to 0. No, you have to maximize it. So this is maximum likelihood parameter. So you have to take derivative of L with respect to all the parameters you have. Okay. So you have to take the derivative with respect to A. You have to take the derivative with respect to what else do we have? We have C also. You can take C also. And what else do we have? We have T naught also. But T naught, no, T naught we have to find out. So T naught is the variable which we need to find out. Is there any other variable? A we have fixed, A naught we have fixed. Sorry, A naught we have fixed. So A we have to find out, C we have to find out. So both of them will be equal to 0. Must be equal to 0. That is how you will be maximizing the likelihood of the phenomena which you are describing. Okay. So then you put all these values, and what is delta? Delta is a censoring scheme. It censors some of the data. Okay. So delta will have a value of 1 when you call your test to be valid based on that criteria. You have a criteria which validates the data for this test or this analysis. Okay. So for all those tests, you maintain that criteria and then you assign delta value and you find out that this test was valid 1. This test is invalid 0. 1, 0, 1, 1, 1. No. Okay. So when it is 1, you will have this contribution. When it is 0, you will not have this contribution. And that's how you will sum it up. Okay. And then by doing this, you will be able to find out the value of A, you will be able to find out the value of C, and then you will plug that there, and then you have solved the problem. Okay. Oh, and also, you can also do the derivative with respect to T naught. And from here, you can find out T naught also. Okay. So a lot of testing and data analysis has been done on ferritic steels, and maximum likelihood analysis has been performed on ferritic steel, especially for reactor pressure vessel steels. Okay. So in those ferritic steels, most of them, they have a value of A is equal to 30. And then you have 0.095 T minus T naught.
ये dl by dt नोट dl by dE के बराबर होगा सर.
dl by dt naught, del L by del A and del L by C, all of them should be 0.
और इन दोनों का डिस्कस अलग-अलग या प्रोडक्ट 0 से दोनों.
कौन सा प्रोडक्ट?
dl by del L by del A.
नहीं, अलग अलग. हर एक पैरामीटर, अगर आपके पास 4 पैरामीटर है ना, तो आप चारों पैरामीटर को मैक्सिमाइज करोगे. Okay, you will find maximum likelihood parameter and then you have to maximize it. It's the likelihood parameter, so you maximize it, and by maximizing it, you find out the values of the parameter. Okay, and then when you plot this KJC versus T minus T naught, when you do that for all the data which I showed, that follows a curve like this, and then you can plot 63.2% probability, 95% and 5%. And all the data falls in this range. It happens. If you don't have this kind of analysis and you just plot KJC versus T naught, you get a huge scatter. But when you do this and plot it, all the data falls on this curve, in this band, all of them. Nothing goes out. Okay, and it is generic in nature. So it can work for any ferritic steel. It will not work probably for non-ferritic BCC alloys. In theory, so for non-ferritic BCC alloys, these values will change. Also, you might have to look for a KJC which is not 100. So if you find out a BCC alloy which has a very high toughness in comparison to ferritic steels, then 100 ampere root meter becomes very less for them. That might happen. For example, for HCP, you will not find out a single test which can give you 100 ampere root meter. So there, this curve is not valid. So there you have to redefine these values. Okay. And I can show you probably in the next class a lot of data which has been analyzed using this, and you will see that it changes. It changes in a very nice way. So all this scatter is shrunk in this curve, and this works for all kind of ferritic steels, generic for any BCC alloys, and all of them has been shown to follow this curve. So it is called master curve. Okay. Master curve is also there in different other areas. For example, you also have a master curve in creep. Okay. So master curve is a general term, but in this case, master curve has become so famous that when you write master curve, people assume it to be this master curve only. And the whole thing where the values are 30, 70 and C is equal to 0.095. All of this has been standardized in ASTM E1921. Okay, and the credit goes to now Emeritus X. Well, he was not a professor in VTT, he was an employee in VTT, now he is a professor. Kim Wallin from Finland. In the next class, I will show you some data, and I will also show you that there has been some cases where researchers, they said that master curve is not good, not correct, it is wrong, and they tested on certain materials and said that it is not solving the statistical distribution. But then there were some other researchers who, so when this standard was made, everyone started following the standard without understanding the background of this. Okay, so if you take just 30-70 value, not all the material will show you a good distribution. So if you are not getting good distribution, then you must do the maximum likelihood analysis again, and maybe you will find a different value of A and A naught minus A. And then the equation will change a little bit, but your distribution will fall in another curve, which will be a specific curve for that material. Okay. So in plane stress condition, we know that sigma 3 is 0, sigma 1 has some value, and sigma 2 will have some value. Okay, so we'll have something like this. This is sigma 2, and what will be tau max? This is tau max, and tau max will be sigma 1 minus sigma 3, right?
Divided by 2.
Divided by 2. Thank you. Okay. So this is my crack tip, and along the thickness I have z direction. This is y, this is x. When it is plane stress, then sigma z is 0. Okay. So what is going to happen? The maximum shear stress is going to take the approximately 45-degree angle between sigma 1 and sigma 3. Right? So sigma 1 is y and sigma 3 is this. So the plane on which maximum shear is going to happen is going to be this kind of planes. Right? On this plane. So what is that plane? That is xz plane. On xz plane, 45, 45, all those possibilities are the possibilities of maximum shear. Right? So in plane stress condition, you will see that you will have shear happening in such a way. So on the back side of this sample, you will see a formation like this. Because of the maximum shearing which is happening. Okay, and this plane will go and it will connect with the so this plane will be something like this, and then you will have another plane. So this is on this side, and then you will have another plane like that, on which, so this will be the plane. Okay, so this is another end of the thickness. Okay, so this is going to drop on that thickness by 45 degrees, like this, right? And so that will be the plane on which maximum shear will be happening. Okay. In plane stress, the things are going to be a little different. So in plane stress, sigma 3 is not going to be 0.
Plane strain.
Sorry, plane strain. Plane stress is explained. Okay. So this is sigma 3, and this is sigma 2, and this is sigma 1. Right? So when it is plane strain, the strain in thickness direction is 0. Right? So you can have a possibility that sigma 2 is the minimum value of principal stress. That could happen. So in that case, this will become sigma 2 and this can become sigma 3. Right? Or wrong?
सर प्लेन स्ट्रेस कंडीशन में सिग्मा 3 0 होता है.
हाँ, प्लेन स्ट्रेस में सिग्मा, इसमें 0 नहीं है. इसमें कहाँ 0? 0 तो ये है ना, ओरिजिन है ना 0. ये तो फाइनाइट वैल्यूज हैं. ठीक है? So you can have a situation where maximum shear stress can be between sigma 1 and sigma 2, not sigma 1 and sigma 3. Right? So in that case, where sigma 1 is this, sigma 2 is that. So 45 degree in xy plane. So how will that look like? So you will have 45 degree like this. Right? तो ये कैसा दिखेगा?
सैंपल के सरफेस पे दिखेगा सर.
कैसा दिखेगा? In that case, on back side, so in that case you will have shear happening like this, and on the back side you will see lines like this, not like that. Okay. So there will be a shrinking also on the back side. Sample will also get shrunk there. कितना टाइम बचा है? 5 मिनट है.
सर एक बार ये दोबारा बता सकते हो सर आप?
क्या?
प्लेन stress velocity.
So it's just very simple that in plane stress condition you have. Why are you asking to waste 5 minutes?
No, sir. Completely different. Because
So in plane stress, one of the stress is 0. Sigma 3 is 0, right? And that is going to be the minimum value of stress. So the maximum shear stress is going to be between sigma 1 and sigma 3. Okay? So that will have an angle of 45 degree between sigma 1 and sigma 3. So like this, along the thickness 45. Along the thickness 45. Isn't it?
थिकनेस प्लेन में थिकनेस के प्लेन में है परपेंडिकुलर
थिकनेस के प्लेन में सिग्मा 1 इधर है, सिग्मा 3 थिकनेस डायरेक्शन में है, तो 45 कैसा हुआ? बिटवीन द थिकनेस प्लेन एंड द सिग्मा y इन द पुलिंग डायरेक्शन एंड थिकनेस, तो 45 डिग्री ऐसा बनेगा, ठीक है? When you have plane strain condition, you might have a situation where it is between sigma 1 and sigma 2, which is in the x direction. So in the ligament direction and in the pulling direction. उसके बीच में
सर ये यहाँ तक समझ में आया सर. उसके बाद ये डायग्राम आपने बनाया था कि शो करने के लिए भी कहाँ पे
हाँ
45 वो समझ में आया सर.
So पीछे के साइड से 45 डिग्री, this is your thickness direction and this is your pulling direction. So in plane stress, if you plot 45, you will have 4 possibilities of 45 degrees, isn't it? नहीं समझ में आ रहा है?
ये सर ऑब्जर्व नहीं कर पा रहा हूँ.
अरे बाबा, ये तुम्हारा एक एक्सिस है, ये एक एक्सिस है, इसके बीच में 45 डिग्री ऐसा बनेगा?
यस सर.
हाँ? अगर तुम्हारा कंडीशन ऐसा हो गया तो ऐसा भी बन सकता है, उधर भी बन सकता है कि नहीं, इधर भी बन सकता है कि नहीं, बन सकता है ना? तो इसीलिए ऐसा 4 डायरेक्शन हो सकता है.
ये हमें सर ऑब्जर्व थिकनेस के मतलब थिकनेस जिस साइड होगी उसके अपोजिट हमें दिखेगा ना, मतलब ये जैसे
ये सैंपल का पिछला हिस्सा है, दिस इज द बैक साइड ऑफ द सैंपल.
क्रैक के
सो द सैंपल इज लाइक दिस.
क्रैक के बिल्कुल सर बैक साइड दिखेगा ना सर.
हाँ
क्रैक के बाद.
हाँ, क्योंकि क्रैक पे इट इज ऑलवेज ट्राई एक्सियल स्टेट, so the plane is going to change and it is going to join the crack tip. Okay, ठीक है? आप 5 मिनट खा गए, 2 मिनट बचा है. So sigma, so now you get an assignment. Okay, so sigma 1, so you know one means, right? Sigma 1 minus sigma 2 summation of sigma I minus sigma j square is equal to 2 sigma naught square, right? And then you put sigma 1 is equal to n sigma 2 and sigma 1 is equal to m sigma 3, and then you put it, replace sigma 2 sigma 3, then you get something in terms of sigma 1. Okay, and if sigma 1 is maximum, then you can define a parameter which is called plastic constraint factor, which is sigma 1 by sigma mesus or sigma naught. Okay, when you put sigma 3 equals to 0, then you get a plane stress condition, and when you put sigma, so no sigma, all of the sigmas are there, so then sigma 3, if you put sigma 3 is equal to mu into sigma 1 plus sigma 2, then you get plane strain condition. So for both of these conditions, you have to calculate the value of PCF in terms of N and M, right? ठीक है? नहीं? बहुत आसान है.
सर सेकंड केस में सिग्मा 2 को n सिग्मा 2 सिग्मा 1 को n सिग्मा 2 लिखेंगे सर.
कौन से केस में?
सेकंड केस में सर.
नहीं, दोनों ही केस में तुम लिख दो ये, बट प्लेन स्ट्रेस के केस में तो ये इसका जरूरत ही नहीं है, right? So sigma 3 is 0. Okay, so sigma 3 is gone from this equation, you have only 2, then you do that, and in plane strain condition you have this relationship. Okay, so m will be a function of mu. Okay, and because it is plastic constraint factor, mu you can put equal to 0.5. Okay, and then you find out the value of PCF for plane stress and plane strain. ठीक है? Okay, done.